Okay, so so we're getting ready to get to talk about the curvature, but so the topic is the speed and how the constant speed affects the curve and what we know about it in terms of motion. Okay, so these are the two things that we discovered, that pretty much constant speed guarantees that the velocity is perpendicular to the acceleration. But so that's good. It seems like a quantity, the relation that is not exactly doesn't seem kind of coincidental. Even though probably you can probably imagine that this picture that we I need to turn on. Why this formula, this one, is so important. Just a minute. This formula in this picture. So why the perpendicular relation is so important. So we take out the constant speed. It allows us to take the speed out of consideration and only concentrate on the change of direction as far as velocity is concerned. And that is how you study curve itself, underlying curve, as opposed to studying the parametric curve. Okay, so that's what we are looking at. As you can see, the rotation is what we are concentrating on only. So like here, same exact magnitude. There is only rotation of the curve. Here's of the velocity vector. So if you're sitting in the car and you can tell which way you're going, that's exactly what you see. You don't see any acceleration as far as you will always feel. You will never feel like when you accelerate, you feel like you're being pushed forward, or if you decelerate, you're pressed into the seat. You only feel the left-right motion. Okay, so that's what it's saying here. Under these ideal circumstances, there will be only the feel of moving sideways. Okay, and this is the idea of how curvature is kind of opposed to the size of the circle, right? So the bigger circle, the less curvature present, and at the extreme, if you keep increasing the circle, the curvature is getting smaller and smaller, and we end up with, in fact, a straight line with zero curvature. Okay, so you can imagine once again, as we're going to show, that the curvature of a circle is 1 over its radius. So if radius is going towards infinity, the curvature goes towards 0. Okay, so so that's the definition of the arc length parametrization. So the parameter t of the we're going to use a specific letter here for the parameter that is arc length parameter s. So to distinguish it from the rest. So the Rs is the arc length parameter. How many arc length parameterization could the curve have? Is it one many or infinitely many? What? No. Once again, when in doubt, go back to the motion interpretation of parametric curve. So, in how many ways can you drive over a road at a constant speed? The answer is the opposite direction. The answer is 2. Okay, so and the result is okay. So the length of the curve is then, in that particular case, is simply the time the time interval b minus a. And this is the very last example that we got into, is the radius, circular radius r. What is the arc length parameter? Okay, so we realized just by experimentation that it is not working out as long as r is not equal to 1. Then we have a not arc length parameter, because as you can see, it is equal to 1. It's not equal to 1. Okay, so so once again, this is the Pythagorean theorem that we did before. Okay, we conclude that the speed is not equal to 1. So then we start to try to figure out what should we do to guarantee. Let me put S here once again to emphasize that we're looking at the arc length parameter. And we realize that for our differentiation to produce a coefficient that would cancel this r, the r is what's standing in the way. All we have to do is just divide the parameter, the original parameter t by r. So as you can see, what has happened here, I'm replacing t with s over r. So once again, t is the original parameter. That's how we drove on the So we were driving. We were driving, in fact, at when this is the standard parameterization of a circular radius r. It is the constant angular velocity. Constant angular velocity term is the turn is always the same over the same period of time. But consider the fact that the radius is bigger, then you cover the longer distance with the same angular velocity. So that seems to be a very standard way to choose the parameterization, but really it's not give us the constant speed. This one will, as you can see, what happens is when I differentiate, I'll have my r is still in the beginning, and then I have r divided by r here, s over r, r over r, s over r, and so I end up with negative sine s over r and cosine s over r, and the magnitude of this is 1. Okay, so yes. So this was a no, and this one is yes. It is the arc length parameterization. So, okay, well, same thing. Let's solve the same problem for actually a simpler situation. And let's take this time a straight line. Okay, so let's say I have f of t is, say I'm going in the direction of vector, say 3, 4. This is the standard parameterization if I know my velocity and velocity vector is 3, 4. So direction 3, 4, and the magnitude is there. So then the easiest way to parameterize such a straight line passing through the origin is just multiply our vector by t. Vector scalar multiplication is what we're looking at. However, if we go with the velocity, now velocity, we already know what the velocity is. It is 3, 4. It is literally the same rule of differentiation that we have in calculus 1, linear function. Linear function differentiate with respect to t, we're left with its coefficient. Okay, except it's not the coefficient anymore, it's a vector. Okay, so it's a 3, 4, and then if we take its magnitude, it will be 3 squared plus 4 squared square root, 9 plus 16, square root 25, it is 5. So, so as you can see, it is 5. It is constant in either case. So even though the answer is no, at least the good news is the speed is constant. But we actually want the speed equal to 1, so the computation would be really easy as far as the curvature is concerned. And okay, so what do we do? A similar idea comes into play. Once again, it appears that we're moving too fast. Okay, that's the same thing as it was there. The radius was, say, if it was, say, 40 over here, and then we realized that we were supposed to move at the speed of 1, and we were moving at the speed of 3, so you divide by 3, and over here, and then we are on the right track. We have speed equal to 1. Same thing here. We're moving at 5, say feet per second. So in order to introduce arc length parameter, we replace t with s over 5. Okay, and once again we have the same story. So g of t is s34 s over 5. This is s over here, and then I differentiate. So I have 34. That part does not disappear. That does not change. And I have 1/5. Okay, and that adds up to. It doesn't really what it adds up to. Will be 305, 405. And one thing, this is a unit vector. A unit vector, and that's what we're after. So that's just another way to say what have been saying, and that is that we want the velocity vector to be a unit vector. Okay, and so in this particular case, it is. You can easily verify that. Okay, so then we have to make this more specific. The replacement, these two replacements have to be now generalized to understand what is it we want and what is the meaning of this as I'd say replacement. What is really am I talking about? Replace one variable with another variable. What does that mean?
Composition.
It's composition. It is a composition. I'm creating a new function, that being the function, and I just substitute it into my function. Then when time comes, even where you can see how I have done it, I'm ending up using the chain rule, right? So every time, I divide by r over here, and that's that over there in that line. I divide by r, and when I differentiate by the chain rule, that's where this thing comes out in the denominator. Okay, so it is in fact about substitution, another good name is especially applicable here. We're talking about change of variables. Change of variables. You'll see why the term is better sometimes in a minute. But change of variables is slightly more specific than just to say we do substitution or composition. So all of these words apply, but change of variables is slightly better. So what we're talking about is then, in the former case, it is t is equal to s over r, and in the latter, t is equal to s over 5. Okay? So, in other words, this is what we're looking at. We're looking at f takes time t to position. Okay, so of any dimension, and then we're composing it with another function which is let's say it's g, another parameter no, and we are that's what we have seen, by the way. This is what we have seen, because we have seen compositions, but they look slightly different. This is what we typically had seen composition when we talked about the chain rule. This was the setup. So a numerical function followed by our parametric curve. Together they form a new parametric curve. As you can see, that we certainly could reduce this situation, the new situation, to that situation. How? By simply doing the well, you can just solve it for s. So s is equal to t times r, and s is equal to t times 5. Okay, so but we can also think about it as a more direct substitution, and so say this is s and this is f, and then what we're talking about. So I don't have a name for it, but the story is pretty much the same. It is more literally a substitution than the previous example. So this is substitution. You do figure out the meaning of the old variable in terms of the new. You have a specific formula, and that is what is being substituted. Right. That's exactly what has happened. What has happened is, so in the latter case, s equal to t over 5, that's the relation that we imagine that we're supposed to be there, and that's exactly what has happened. This is, as you can see, that's exactly what has happened is we substituted, so we had f of t to begin with, and then we transitioned by p is equal to f of t, and then we substitute the value of t, the old variable, in terms of the new variable. So, and then we ended up with p is equal to f of, say, s over 5. Okay, and that was the new parameterization of the same curve. Okay, so the only thing that to worry about is, and that is how we have to be careful about the meaning of the change of variable rather than general substitution. First, let's think about this for a moment, and it becomes clear what happens here is this. Well, there are more extreme cases. Let me do one more example of this. So, for example, another example is, suppose I'm moving around this circle, but well, let's go with a straight line. Suppose I am speeding up. So I have my, say, 1 f of t is equal to say t squared t greater than or equal to 0. Okay, so what is this? What is this curve?
Isn't it just a line?
It is a straight line, indeed, but what's so special is we have a different parameterization. So this is a curve. The curve itself looks like this. It is indeed a straight line, but the parameterization is not linear. So straight line, non-linear or non-uniform motion. Non-uniform accelerated motion. As you can see, I'm going faster and faster and faster. So if I try to plot the two component functions, they both the parabolas. So in other words, if I want to plot not just the curve, that's the curve. This is the road. Okay. So if I'm looking at now at my motion, it will look like this. So 0, 1, and then at the units of time, unit of time is the same, but the distance, no, that is slowing down. I'm sorry. Okay, and then I'm making bigger and bigger leaps every second. So this is the first leap, and then I make a bigger one, and the bigger one, and the bigger one. Okay, so the once again the leaps are getting bigger and bigger and bigger. Okay, so let's ask ourselves the same question: what is the arc length parameterization? You could speak of the arc length parameterization if you know the direction. So every parametric curve has a direction. Okay, and then if you want to come up with a parameter that has this requirement of the speed equal to 1, then it is logical that to parameterize it in the same direction. So if the direction is determined, this is a curve with indicated direction from the beginning to the end. Same can be done with a circle, one way or the other. So then there is only one parameterization. Okay, so what is the arc length parameterization? We look at well, this time, let's work it out. F prime of t is equal to then 2t, and it's the magnitude then of the velocity or the speed is 2 square of t. Okay, so as you can see, it is increasing, going faster and faster, as you can see on that picture. So, all right. So, what should be our change of variables? which is, once again, in the direct way, t is equal to, let's say, a g of s. Okay, so we don't know what it is. Okay, and then what's supposed to happen is we substitute and go through the same computation, then we're supposed to end up with 1. So compose this function with the to make a function of t that we'll have a function of s, and then we'll see what happens. So then we have g of s is equal to f of g of s. Okay, and that's okay, and then which is 2g of s, okay. In fact, at this time, if you really want to make life easier, 2g of s, 1, 1. Okay, so that is our new parametric curve, which g is still to be found. That g little is still to be found in order to make it arc length parametrization. So we take we differentiate. Okay, so that's why that simplification is worthwhile, because now I simply have 2g prime of s, assuming the function is differentiable, and that coefficient does nothing. It is just the direction. Okay, so I take the magnitude of this. G prime of s is equal to 2 g prime of s 1, 1. No, I'm sorry. I didn't substitute in the right function. I was supposed to substitute into f. Sorry about that. I substituted into f prime. Okay, so okay, we'll have to redo some stuff here. The original function is at the very top, and I'm substituting into that one. So it will be g of s squared, and the other one is also g of s squared. Okay, so that's what we're talking about. Squared. Okay, so now I'm differentiating, and now that's where the chain rule comes into play. Okay, so but I could still do what I did in the g, because it's the same thing. Gs squared 1, 1. Okay, so then my differentiation will be entirely numerical, not vector differentiation. So what's the derivative?
G prime s.
2gs g prime s times 1, 1. So the numerical part, and then how much this vector is stretched by this much. Okay, so now I'm computing the magnitude. So it will be simply 2 g of s g prime of s. I'm assuming, just to keep it simple, that g is positive, and as well as its prime is positive too. So it is an increasing positive function. Let's suppose our substitution is that. And then it's simply multiplied by the square root of 2. Okay, norm. Okay, and then this is supposed to be equal to 1. Okay, so what remains is now I'll figure out what that function is. So any suggestions? What should g be? So let me write it once again. G of s, g prime of s is equal to, what is it? 1 over 2 squared root of 2. So the coefficient on the left is really not that important. It is in fact this thing has got to be a constant, at least the specific constant is to be determined. But you can figure out what this is if you just think about So function multiplied by its derivative is constant, other than 0. Can you think of such a function?
I mean, the function itself has to be linear then, right?
No. In fact, it cannot be linear. It is linear, works out every time.
Okay.
In these two examples, the linear substitution, linear change of variables worked out because the only reason was because the speed was constant. The speed was constant, say 5, and that we needed this extra coefficient that we plugged in where it was necessary, 105, to adjust, and then everything works out. But in this new example, in fact, we are accelerating, and our speed is not constant, unfortunately. It is 2 squared of t. Okay, so which means that the linear substitution won't work, and it certainly wouldn't satisfy this condition either. Right. So once again, can you think of a function the derivative of which is well, pretty much reciprocal of the function itself?
Square root.
Square root. That's right, square root. Square root of x prime is 1 over 2 square root of x. And you can see that we could have guessed that because of those squares to begin with. If you try to adjust that, you want to convert t squared into t, roughly speaking. And then how do you do it? Well, you take the square. So that certainly is something that we could have anticipated. So it's almost the same function up to a coefficient, and that how it works out. So let's see, does it work out exactly? So it's so what is g of s then? It's not exactly square root of s, but rather what is it? 1 over square root of 2 square root of x, 1 over 2 square root of x, I think. Well, let me check it out. So g prime of s is 1, hold on a second, I meant in the numerator, square root of 2x. Or is it x over squared? It is x over 2. So it's square root of x with a coefficient, and we just, it is my impression that it's x over 2. So then it's going to be 1 over square root of 2 square root of x, and the 1 over square root of 2. Okay, yeah, it checks out. Right? Does it check out? Yeah, no, that doesn't check out. I think it is. I think 1/2 is. This is. I think it's something else. One-half square root of x. Okay. Let's just take one more for it. Okay, so that's the substitution. Just a good example of a function that is not necessarily a linear function. A substitution, the function looks like this, right? Roughly. What is good about it is actually these two conditions. And these are the two conditions that are kind of important to what we're trying to do, and that is the change of variables. It's like, imagine that let's take this example again, and suppose what we have here, we are trying to study this curve, this road, which is a simple one, but still we don't know yet. So and then we ask some driver to drive through it and take a video, okay? But he was driving that way, he was speeding up, okay? So the question then becomes, we want to study in a kind of uniform way, and we want to retime the video in such a way that it would appear to us that we are moving at a speed of 1, say, mile per hour. Okay, that way we will apply some algorithm that will study the curve analytically or numerically, and then we'll find out what we want. So then this function g that we found is in fact retiming of the tape. So usually when you have some kind of a video software, so you can go slow motion, fast motion, but not typically variable. Slow, faster. This one we certainly might want to require that, but there might need that. But we do have to require something about this, about that change of variable that would be reasonable. And that this is pretty much is the condition. The second one especially. The second one especially. So you do not want to. If g prime is negative, what does that produce? G prime is negative at some point. What does it mean? Positive and negative.
It's decreasing.
It keep increasing, and then at some point it's decreasing, which means that we will revisit. We are watching that video, process video, and we'll see that as if we're moving forward and then backwards all of a sudden. So we don't want anything like that to happen, because that will mess up all our information about the road. So it's not really as much as about the derivative, but what's the word that we actually want to save here about the change of variables. The change of variables should be, what kind of function should it be? One to one, yes.
In that final statement of G of S,
What?
in that final statement of G of S, down just a bit, yep, the one that's bracketed.
Yeah.
Do we want that to be 1/2 square root of t?
Oh, T, yeah, thank you. That's right. Okay, yeah, so, hold on a second, where did I, my variables are messed up. This is of S, as a matter of fact. Our function is of the new arc length bracket. T equal to the arc length bracket. Okay, so well, another way to see it is simply to recognize the relation between the three quantities. So what is the relation? Between the T, S, and P. So we have from T to S, that is our G, okay, and then this is my P, and then this is my F, the original parameterization, and this is my G. Okay, I'm not sure if you've seen the diagrams like this before. It is not just establishing the relation between the functional relation between the quantities, the variables, but also it indicates compositions. Okay, so G, as you know, as we build it, is the composition of F and G. Okay, so G followed by F. So that's these are called commutative diagrams. They're very popular in some areas of mathematics, but they are very convenient to establish the relation, the functional relation between quantities. And this is the G on one hand. You can go as a composition like this, okay? A composition like that. So G followed by F. Then you come from S to P, and that's the new parameterization. Or you go straight. Okay. So these two routes. And that's where the word commutative comes from. These two routes are identical. So, I mean, if you are moving in a city on the grid, then if it is a perfect grid, you can go like this. right? Or you can go like that, and it will take you, this is exactly the same, and the time it takes to commute is also exactly the same. Okay, so that's where the meaning of the word commutative, if you like. But in this particular case, slightly simpler. It is a triangular diagram with 3 quantities. You can have more than that, as many as you like, depending on the size of your composition. And then, like I said, we indicate that getting from S to P can go directly through G, or you go with the composition G followed by N. That is not new entirely, and the preferable way of dealing with this is remember that sometimes this is certainly what it's about. It's about compositions. It's also about, if we are getting to derivatives, it's also about the chain rule. And you could either write the chain rule from here to say G dg ds is equal to df dt dt dg ds. Okay? Chain rule. So that is the relation between these two, and from the chain rule, okay, and then if I take the magnitude, the magnitude that I'm looking for here is dg ds is in fact 1, okay, so the magnitude of that velocity vector, so which means that the magnitude, the product of the magnitudes, I don't believe we have discussed that. So this is, by the way, is just a multiplication. This is just multiplication, because df dt is certainly a vector, is a parametric curve, but the second one is a scalar, right? The change of variables is a numerical function. So we'll have this multiplied by, this is the homogeneity property, and we have this little formula. So let me try to write it out in terms of the formula. So let's say, suppose P is equal to F is the parametric curve. Differentiable. And G is equal to T is equal to G of S is the change of variables. Also differentiable. Then, as we can see, we have this formula, the relation between those quantities. So the velocity, the speed of the original parameterization times the magnitude of the substitution, which helps us to actually find what, not the magnitude, the absolute value of the substitution, which will help us to find what it is equal to 1. Okay, so if we are knowing the magnitude, the absolute value of the derivative tells you pretty much all you care about. Well, in fact, let me erase this negative sign, the absolute value sign. I think it's just confusing the issue here. So let's just say g of t is, let's say it's positive. Okay, so then, well, that's the relation. The derivative that we're looking for, we found in that example we just did. This is what you find the derivative, you find g by the differentiation naturally. And so if you know this, you can. So the original parametric curve is given. You differentiate. You take the absolute value. That gives you the reciprocal of the derivative of the change of variables. So in fact, let's verify that it works out with the example we just had. So dg ds was, well, that's what we're looking for. df dt was 2 over square root of t. Okay, so that f prime here, I'm using the Lagrange notation. I'm sorry, Leibniz. This is Lagrange notation. This is Leibniz notation. So 2 square root of t. So this is 2 square root of t. Okay, and then so it means that my g prime of s is equal to 2 square root of t, except we still need to I'm not sure if it helped a lot. Does that make sense? Okay. So the derivative, no, that doesn't. That doesn't make a lot of sense. I'm sorry, the reciprocal. I forgot the reciprocal part. It is then 1 over this thing. D prime of S is 2 square root of C, and so 1 over 2 squared. 1 over 2 square root of T, or 1 over 2 square root of G of X. Okay, well, so maybe I'll sort it out a little bit better next time. One thing that is easy to conclude, well, let me actually pick a simpler example that should work out easier, and that is the straight line. Okay, so suppose we have a straight line. How do we quickly reparameterize it? We already know the answer roughly, but let's do it anyway. So I have my straight line, which is P of t is equal to, say, some vector t times t. By the way, I could add an extra vector here, say P naught, okay, to indicate the initial point of my line, but it will not affect the neither speed nor curvature, so I'm throwing it out. So suppose this is my parameterization in any dimension of a straight line. Okay, so then I'm sorry, this is f of t. If I want to use the same notation, f of t. So then f prime of t is v. And so then, well, actually, we don't have to do any work here. It is just the magnitude of the velocity. Then the speed is in fact the magnitude of v. So then we can conclude that well, let me put it this way: parametrization f of t equal to vt is an arc length parameterization. If and only if the magnitude of v is equal to 1. Okay, that certainly is predictable. Okay, so I have a few minutes left. Let me start this example that I was going to do. We will continue next time, but let me get started. Okay, so this is a circle, and what I want to do is parameterize in the usual way. What I want to do with it is to compute the speed as well as compute the whatever happens to the arc length parameterization, and then I'll use the same picture to compute the curvature. Okay, so let's do, so it's just a standard circle. Let me compute the speed. Okay, so I'll put here x prime, not literally. This is not literally x prime because these will be just the difference quotients, as we have done a few times. Okay, so difference quotient. This one is equal to the difference of the two consecutive values of y. Of x. Okay, so I forgot to divide by h. And the dd has to be divided by the length, which is over there, row 6, column 1. Okay? So that is, as you can see, indicates the decrease. Okay, so we'll just spread it out. Okay. Okay, Okay, so these are my velocity vectors. Technically, they're just the velocities of one point to the next. So these are average velocities. So I put x prime there, but just average velocity. Now let's find the speed. So what's the speed? We have two components of the velocity right there. Average velocity, but still. So we're talking about still average speed. So all of these is average. I will compute it. These are all average. Okay. So how do we compute speed from the two components of velocity?
Just use the Pythagorean theorem.
Right. Well, yeah, we have a formula. So square root. Oops. Of the sum of the squares of these. Okay. Let's see what happens. What do you know? It's all one. Okay, so speed is 1. Even approximate speed is still 1. So if I change, however, let me change this first into an ellipse. I still have some time. If I change it into an ellipse, unfortunately, Excel resizes the window, so you cannot see that it is an ellipse, but you can see it goes up to 1 and wide to 2. And you can also see how the speed is not constant anymore. Okay, so even in the simplest situation, I put 2 here. You see what happens. Now this is a circle again, but the speed is not equal to 2 anymore. Okay, so let's find a new reparametrization, the arc length parameter. Arc length parameter will be here. I'll put once again x and y, and so what do we do with it? How do I get the well, I'm not going to reparameterize. I will have x prime, y prime here. So what the plan is to look at the unit, make the velocity vector into a unit vector, and look how fast it is changing, and that will give us the curvature. Okay.